Hello. So here I explained the motivating example for a linear regression model. So the idea is, again, the key idea is we group the data by student-teacher ratio and calculate the group-wise within-group averages, which is more formally called the conditional expectation. And then we draw one straight line that goes through those averages. So we summarize the data into these two steps: conditional expectation and approximate by a line. And let's use more equations, more formal notation. So the population regression line. So in the motivating example, I used 50 observations, but so remember the difference between sample and population. The sample is finite observations, and the population is infinite number of observations. So I could not handle infinite number of observations, and there is nothing like that in reality. So it is just an imaginary object, but population regression line is, so if you increase the sample size, the number of observations in this example, and in the limit, then it will be the infinity. In the infinite case, think about what the line will be. That's the population regression line. And that's unknown, of course unknown, because we cannot observe an infinite number of observations, but still this is what we want to know. So we write the population regression line in this way: test score equals a linear function of student-teacher ratio. So beta 0 plus beta 1 times student-teacher ratio. That means beta 1 is the slope of population regression line, which means when student-teacher ratio increases by 1 unit, then test score will increase by beta 1, right? So when you increase this by 1, test score will increase by beta 1. That's the meaning of beta 1, right? So this is, and beta 0 and beta 1 are what we are going to estimate, and especially we may be particularly interested in beta 1. Then why do we call them population parameters? I explained. This is the true relationship. So I said true because we imagine an infinite number of observations. So if we could observe an infinite number of observations, then we can learn about the true relationship between beta 0 and beta 1, between y and x, between student-teacher ratio and test scores. But so that's our target. We would like to know these two population parameters, and we assume that the true relationship is given by those two numbers. And as I said, we are summarizing everything into these two numbers. Beta 0 and beta 1 will explain the relationship between these two variables no matter how many observations you have. So it's a huge simplification and will help computation and presentation. So help you better understand the trend in the data. So So we would like to know the population value beta 1 in many cases, but as I said, we do not know that. So we have to estimate it using data. So using finite number of observations. So using finite number of observations, we would like to know the value that would happen if we had an infinite number of observations. Right? So, and then why are we interested in that? So linear regression line is the meaning is the expected value of y given x. So if you want to understand the expected value of y given x, then the regression can help. For example, the slope is the difference in the expected values of y for two different values of x. So as I said, beta 1 can be understood like this. So suppose that the student-teacher ratio is now 20. And what happens? What would be the change if you increase the student-teacher ratio to 21? If you increase or decrease, lower the student-teacher ratio to 19? The answer is beta 1, right? So you can put it this way. What is the expected test score when the student-teacher ratio is 20? And what is the expected expectation when the student-teacher ratio is 21? Their difference is exactly the same thing, right? The difference between two expected test scores between 20 and 21 is the change when you increase the students ratio by 1. So you may understand the regression in that way. That's an easier way to understand what we are going to do. It's a kind of expectation. And more formally, you may say something like this. We would like to do causal inference. When you increase the student-teacher ratio, what if you can do an experiment with the student-teacher ratio, what would be the outcomes? What would be the results, consequences of those experiments? That's causal inference. Without doing the experiments, you may use the data to guess, to infer about those causality, the cause and effect relationship between test scores and student-teacher ratio. Also, prediction, pretty much the same thing. You would like to predict what would happen if I reduce or increase the student-teacher ratio, and then you can measure how well you are doing, or you can evaluate how good, if the school is performing more than expected or less than expected, something like that. So prediction and causal inferences are two most common and maybe the only two reasons why we use to proposes goals of regression models. They are different, but the difference is quite subtle. So I'm not sure if I will have a chance to talk about their differences, but basically they are using the same regression models. So different applications use the same regression model but take a little different approaches depending on their purpose, so whether they would like to study causal relationship or whether they would like to predict something. So, but for a while, maybe in this course, you may just think them in like they are basically the same, using the same regression models. That will be fine, I guess. And then statistical inference. What kind of inference methods do we need to use? Are we going to do? The linear regression, the statistical inference for linear regression can be understood as the statistical inference for the mean, right? Because basically we are using conditional averages, so that's just a kind of averages with a little variation from the simple averages. So you can in the end you can apply all the methods you used to infer about the mean to the regression models. So for example, in terms of estimation, you would like to estimate beta 0 and beta 1. And later you are going to see that those two guys have striking similarities with the sample mean and the inference methods for estimator for the sample for the population mean. And in regression, we put that. You may just think that in this way: how do we draw a line through the data to estimate the population slope? Basically, as I said, in the end, it will be very similar to estimating the population mean. And the answer is ordinary least squares. Least squares methods is applied, and we'll be talking about that pretty soon. And we need to study what are the advantages and disadvantages of this method. And you may think about hypothesis testing. Does it have, so for example, you believe that student-teacher ratio has no effect on test scores. Is it right? Can you reject it? Or if you believe that student-teacher ratio has a negative impact on test scores, then you can test it. So the hypothesis testing, it's also going in the same way as a hypothesis testing about the population mean. So hypothesis testing about the slope, regression slope, is very similar to hypothesis testing about the population mean. And confidence intervals. What are the confidence intervals for the slope? Or what are the margin of errors for the slope estimator? Also, it will be very similar to the population mean. So so you may just think it this way. I teach the basic inference methods for the population mean in eco420, and that actually you may have thought that the population mean inference is too simple, too easy, but actually it has a lot of applications like this. Regression model can be understood as an application of inference about the mean, but it is much more useful. So I want you to see the connection between them. You do not need to know the details of the proofs or mathematical derivations. I'm going to show that, but I don't expect you to memorize them. But anyhow, if you understand how we handled the population mean inference, then that will surely help you understand the regression model inference. Okay, thank you for watching. We'll continue in the next video.